We previously discussed the dot product in great detail. This is an operation on two vectors in Rn that produces a scalar. We saw several of the important properties of the dot product and saw how the dot product can be used to define the angle between and the distance between two vectors, as well as the length of a vector in Rn, which expanded our understanding of angle and length beyond 1, 2, and 3 dimensions to any number of dimensions, since the definitions were for Rn in general. Now, those concepts of the angle between vectors and the magnitude or length of a vector, those are important in vector spaces outside of just Rn. And in order to make sense of those concepts in general vector spaces, we're going to need some sort of operation like the dot product. And that's what we're going to be introducing today. It turns out the dot product is just a common example of what's called an inner product. In this video, we'll go over inner products and inner product spaces. We'll see several examples and non-examples. We'll do some computational practice. We'll see some algebraic properties of inner products and see how they can be used to define the magnitude of a vector and the distance between vectors in general vector spaces. This video has chapters, so you can skip around as you please. Here is our definition. An inner product on a real vector space V is a function that associates a real number, written like this with angle bracket notation, with each pair of vectors in V, and satisfies the following axioms for all vectors uv and w in the vector space and all scalars k. We're talking about real vector spaces, so these would be real scalars, but this could all be extended to complex vector spaces as well. So these are the four properties that a binary operation on a vector space has to satisfy in order to be an inner product. Note that they're just ripped straight from these basic properties of the dot product, because in some way this is a generalization of the dot product. As long as an operation works like the dot product, it is what we call an inner product. An inner product has to satisfy the symmetry axiom. The inner product of u with v has to equal the inner product of v with u. If we were talking about complex vector spaces, the axiom would look like this. The inner product of u with v equals the conjugate of the inner product of v with u. In the case of real vector spaces, conjugates don't actually change anything, so we could just as well use this axiom in place of this one for our real vector spaces, but there's not really a point to doing that. And that first axiom is the only one that would look different for complex vector spaces. The rest of these would be the same. And for the rest of this video, we're just going to talk about real vector spaces. The second axiom is the additivity axiom, so we can split an inner product across a sum in the first slot. The inner product of u plus v with w is the inner product of u with w plus the inner product of v with w. Third, we have the homogeneity axiom, so a scalar can be taken out of the first slot. The inner product of ku with v is k times the inner product of u with v. And fourth, we have the positivity axiom. The inner product of a vector with itself is non-negative, and the inner product of a vector with itself is only equal to 0 in the case where the vector is the 0 vector. Some questions you may have, like does homogeneity apply to a scalar in the second slot, and does additivity apply to a sum in the second slot, will be answered when we look at some algebraic properties of inner products. So that's what an inner product is, and of course, if we have a real vector space V with an inner product, that's called a real inner product space. If we have a real inner product space, then things like the magnitude or norm of a vector, things like distance between vectors and angle between vectors, are things that we can make sense of using the inner product. The most common inner product space, which we have experience with, is Rn with the typical dot product. That's called Euclidean n-space. And you may recall how in Euclidean n-space, we use the dot product to define the norm and the distance. We had the norm, or magnitude of a vector, defined as the square root of the dot product of the vector with itself. And the distance between two vectors was the magnitude of their difference, which again just comes back to that dot product. In the exact same way, we can define norm and distance in a general inner product space. If V is a real inner product space, then the norm, or length, of a vector in V is denoted with the double magnitude bars around V, and is defined as we would expect. It's the square root of the inner product of the vector with itself, denoted with those angle brackets, since the dot notation is reserved specifically for the dot product. And as usual, if a vector has norm 1, we call it a unit vector. We also have then that the distance between two vectors is defined as the magnitude or the norm of their difference, which just goes back to the square root of the inner product. All of the basic properties of norm and distance, which were true in Euclidean n-space, also hold in a general inner product space. The magnitude or norm of a vector is at least 0, and the norm will equal 0 if and only if that vector is the 0 vector. The norm of a scalar times a vector is just the magnitude of the scalar times the norm of the vector. The distance between two vectors is not affected by changing the order in which the vectors is listed, and distance is non-negative, equal to 0 only in the case where the two vectors are equal. These properties all follow pretty simply from the definitions and from the axioms for an inner product. I'll leave links in the description to videos going over these properties with proofs. Before we see our first fresh example of an inner product space, let's take a look at a non-example. How could something fail to be an inner product? Well, let's take two arbitrary vectors from R cubed, where u is equal to this and v is equal to this. And then let's define this product, which we're not going to call an inner product because we're actually going to show that it isn't one. But let's define this product as follows. The product of u with v is equal to the product of their first components minus 2 times the product of their second components plus the product of their third components. This is pretty similar to the dot product, it's just that this second term has that factor of -2. And it's precisely because of that -2 that we'll be able to show this is not an inner product. Recall that the fourth axiom for an inner product is that the inner product of a vector with itself has to be non-negative. But if we let u equal this vector, 0, 1, 0, then if we take the product of u with itself based on this definition, well, the first and third terms are just going to be zeros, but the second term is going to be -2 times 1 times 1, and so the resulting product is -2, which is negative and hence violates axiom 4. So this is not an inner product, hence R cubed with this operation is not an inner product space. And if this were our function, our definition of norm would not make any sense. If we tried to find the norm of u, which is supposed to be a real number in some way measuring u's magnitude, that would be the square root of the product of u with u, but in this case, of course, that product is negative, and there's the problem. Now let's take a look at a non-standard inner product on R squared. So not only are there other types of operations that behave like the dot product, but there are also such operations even in Rn. One such example is the Euclidean weighted inner product, and this is one of those. So if we take two vectors in R squared, where u is that and v is that, we could say that the inner product of u with v is the product of their first components plus 2 times the product of their second components. Again, this looks like the dot product, but the second components are weighted more heavily, hence the term weighted Euclidean inner product. Now, we'll go through the 4 axioms for an inner product and verify that this satisfies all of them. First, we have the symmetry axiom. The inner product of u with v should equal the inner product of v with u. We can demonstrate this very easily thanks to the commutativity of multiplication on real numbers. u1 v1 is the same as v1 u1, and 2u2 v2 is 2v2 u2. So clearly, the inner product of u with v also equals the inner product of v with u. Next, we'll show that this product satisfies the additivity axiom, that we can split the product across addition in the first slot. For this, we'll need a third arbitrary vector, call it w, and denote its components like that. Then consider the product of u plus v with w. By definition, this equals the sum of the first components of u and v multiplied by the first component of w, plus 2 times the sum of the second components of u and v times the second component of w. Then we just apply some distributive property and some shuffling things around by the commutative property of addition, and we're able to rewrite this whole thing so that we have the product of u with w plus the product of v with w. And so we see that this operation, as defined, does satisfy the additivity axiom. Next, we'll show that it satisfies the homogeneity axiom, that we can take a scalar out of the first slot. So consider the product of ku with v. By definition, that's equal to k times u1 v1 plus 2k u2 v2. But then by the distributive property, we can just factor out that scalar k and write this as k times this sum. This sum is precisely the product of u with v. And so we see that we're able to take that scalar out of the first slot, so the product does satisfy the homogeneity axiom. Lastly, we show that it satisfies the positivity axiom. The product of v with itself is equal to the product of its first component with itself, plus 2 times the product of its second component with itself. Thus, what we have is a sum of squares with a positive factor. This is clearly non-negative because it's just squares and that positive factor of 2, and it could only be 0 in the case when v1 and v2 are both 0. That's the only way that this sum would be 0. Of course, that would mean that it's only 0 when v is the 0 vector. Hence, this product does satisfy the positivity axiom, and so it satisfies all 4 axioms for inner products. Hence, it is an inner product. And R squared, with this operation, is an inner product space. And so, just as with the dot product, we can consider the length of vectors in R squared, or the distance between vectors, using this inner product. We could also consider the angle between vectors, but we'll go over that in more detail in a future video, link in the description. For now, let's take a look at norm and distance in this new inner product space. Let's let u be the vector 1, 0, and v the vector 0, 1. Then by definition, the norm of the vector u in this inner product space is the square root of the inner product of u with itself. That's the product of its first component with its first component, 1 times 1, plus 2 times the product of the second component with the second component. This ends up just being the square root of 1, which is 1. And so the norm of u in this inner product space happens to equal its norm in the traditional Euclidean n space. Its norm is just 1. V, on the other hand, since it has a 1 in the second component, which in this inner product space is weighted more heavily, the second component's weighted more heavily, the norm of V is not going to be 1. As we see, its norm is the square root of the inner product of V with itself, which is just 0 times 0 from the first component, plus 1 times 1 from the second component, but doubled. And so its norm is root 2. This new inner product will also change the distance between these two vectors. You may recognize that in traditional Euclidean n space, the distance between these two vectors would be root 2, but in this weighted Euclidean space, we have the distance being the norm of u minus v, and that of course is the square root of the inner product of u minus v with u minus v. U minus v is just 1, negative 1, so what we see here is the square root of 1 times 1 from the first component, plus negative 1 times negative 1 from the second component, but multiplied by 2. So under the square root, we have 1 plus 2, and so the distance between the two vectors is root 3. So again, since the definitions of norm and distance depend on inner products, the norm of a vector, or the distance between two vectors, will depend on the inner product being considered. Even in a single vector space, there are many inner products we could consider. Here are some useful algebraic properties of inner products, link in the description to a video proving these. They follow pretty simply from the axioms of inner products. The inner product of the zero vector with any vector v will equal 0. We actually have additivity in the second slot as well, so we can split an inner product across addition in the second slot. Same thing is true for subtraction. We can split an inner product across subtraction in the first or the second slot. And homogeneity applies in the second slot as well. We can pull a scalar out of the second slot, just as you would probably like. Let's try using these properties to do a simple computation. Let's say the inner product of u with v equals 2, the inner product of v with w equals -3, and the inner product of u with w equals 4. The norm of u is 1, the norm of v is 3, and the norm of w is 5. Using all this information, let's evaluate the inner product of 2v plus w with 3u minus 2w. In order to do this, we'll take this inner product and then apply algebraic properties to rewrite it in terms of information that was given. First, we split the inner product across that subtraction in the second slot. So we have 2v plus w, 3u, minus 2v plus w, 2w. Then we'll split each of these inner products across the addition in their first slots. So we have the inner product of 2v with 3w, then w, 3w, those are being added, that's the first one. And then minus, in parentheses, we split this across that addition as well. So the inner product of 2v with 2w plus the inner product of w with 2w. Then with this inner product, we take the scalar of 2 out and the scalar of 3 out. So we end up with a factor of 6 outside. With this inner product, we take that scalar of 3 out. And then with this inner product, we take both factors of 2 out. So we see a scalar 4. And then with this one, we take that scalar of 2 out. Now, the inner product of v with u was not given to us, but the inner product of u with v was given to us. And of course, by the symmetry axiom, those two things are equal. So the inner product of v with u is equal to 2. The inner product of w with u is the same as the inner product of u with w, which is 4. The inner product of v with w is -3, so we replace that. The inner product of w with w is not exactly given to us, but it's very closely related to the norm of w. Remember, by definition, the norm of w is the square root of the inner product of w with itself. So by squaring both sides, we would find that the inner product of w with itself is just its norm squared. Hence, this inner product of w with itself is just equal to 5 squared, or 25, which we see there. 6 times 2 is 12, 3 times 4 is 12, 4 times -3 is -12, 2 times 25 is 50. Then just do all this addition and subtraction, we end up with -14. That's this inner product, evaluated using some algebraic properties. Finally, let's look at an inner product on a vector space other than Rn. This is called the standard inner product on the vector space of square matrices. So if u and v are square matrices from this vector space, then the inner product of u with v is defined as the trace of u transpose times v. Recall that the trace is the sum of the diagonal entries, and this is an inner product on the vector space of square matrices. For an example, let's see what it looks like for 2 by 2 matrices. Here's an arbitrary 2 by 2 matrix we'll call u, and here's an arbitrary 2 by 2 matrix we'll call v. By going through this computation, you'll see exactly why this inner product actually makes a whole lot of sense. To find u transpose, we just have to swap the rows and columns. So the first row becomes the first column, the second row becomes the second column, and then this is getting multiplied by v. Now if we do this, what we're going to have is u1 times v1 plus u3 times v3. That is on the diagonal. Then the next entry doesn't really matter because in the end we're going to take the trace, which means we're adding the diagonal entries. The next entry also doesn't really matter because again we're going to be adding diagonal entries, and the next entry is not on the diagonal. But then finally this last one is on the diagonal. It's u2 times v2 plus u4 times v4. Now if you look at these diagonal entries, you may notice that the terms actually match up. u1's getting multiplied by v1, u2's getting multiplied by v2, U3 is getting multiplied by V3. U4 is getting multiplied by V4. So when we take the trace of this, which is the inner product, it requires that we take the trace, it actually looks just like a dot product. So in this vector space of 2 by 2 matrices, we see that the inner product of U with V, which is defined as the trace of U transpose times V, is actually just the sum of the products of the corresponding entries of the matrices. This is just the dot product of those corresponding entries. As a result, it's pretty straightforward to verify that this is indeed an inner product. I'll leave a link in the description to a video going over this standard inner product in more detail. But that is a thorough introduction to inner products, inner product spaces, and some of the relevant properties and definitions, and some basic examples. Let me know in the comments if you have any questions, and be sure to check out my Linear Algebra course and Linear Algebra exercises playlists in the description for more. If you find these videos helpful, please consider supporting what I do by joining Wrath of Math as a channel member. You can get access to lots of additional practice and exclusive videos, and access to these lecture notes if you join at the premium tier or above. Thanks for watching.
Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about. Stressed out, honey, I've been stressed out lately. Don't know what's what, don't know what I'm stressed about. Stressed out, sweetie, I'm stressed out. Sounds like you've been stressed out. Tell me what you're stressed about.